of our exposure series. So today's speaker is Suresh sir. Before that, I invite Suresh sir, Lady madam, and office bearers, and also all dear students. I'll just brief you about Suresh sir, because after the last meeting, some of new students would have joined. Couple of students would have joined later. So I'll just give us brief introduction about Suresh sir. He has completed his BTech from MA College of Engineering in the year 85. And thereafter, he completed his MTech from that. He has completed it with a rank from Mahatma Gandhi University, MA College of Engineering, and then he went to IIT Chennai. There he completed his MTech in structural engineering and worked at IIT for quite some time as a research assistant, project assistant, and then started his firm in Kerala. So we are very fortunate to get somebody so highly talented to work back in India for us. Because most of the people those times who completed from IIT never came back to India to work for us. And then after he started his office, he has worked in most of the areas of civil engineering, starting from not even starting with, it's actually all the areas of civil engineering, infrastructure, commercial, residential areas, buildings, infrastructure projects, steel, pre-stressed, RCC, everything. He would have done, around 3,000 plus projects in structural designing, and more than that in foundation side, and the list is endless. We may require quite some time to cover all the area. But for us, the most important thing is that he has a special interest in transferring the knowledge to other people. So whenever we had questions, there was always one person to ask for. So, I remember those days, when we worked as a, colleague in the same area. It is very difficult for somebody to, give the knowledge or transfer the knowledge. So this is a very big speciality of Suresh sir, that whatever problem that comes, he will take a paper and pencil and he'll make sure that you understood these things. So this is something very, very important for us, and it's a real opportunity. He has, covered a lot of series, a lot of seminars, discussions, and most of the areas of construction, spreading knowledge to all the areas of people. That's including faculty, students, researchers, and commercial establishments. People working in the industry side. So with this, I conclude, and I invite Suresh sir to give you basics of structural engineering. And this is, will be a wonderful course for you. It will be he has agreed to give a series of lectures. So this will be building blocks for you so somebody who wants to understand, to make things very simple. This is the channel. This is a golden opportunity. You have to tell your friends also to join and use this opportunity and this, classes to the maximum. Thank you, sir. So with these words, I invite Suresh sir. Thank you.
Thank you, Raji. Thank you for your kind words. It's a pleasure that I could talk to the students. And I think we'll try to share our past experience, and we may touch upon certain theoretical side as well in between in the series. We'll put a basic. Raji, shall I share my screen?
Yes, yes.
Is it visible?
Yeah, clear.
Okay.
Yes.
So we will have a basic introduction of basics of structural engineering to our students, so that those who work whatever the field in which a civil engineer works, they should have a basic knowledge of structural engineering, because whether it is transportation, whether it is environmental, everywhere a part comes as structural things. So the basic knowledge of behavior of materials and structural systems is essential for a civil engineer to perform in any field of civil engineering. So I will try to do this civil engineering students a basic introductions on structural engineering. During this course, we will try to cover what is a structure and what is structural engineering, why and how. Means we should know the load path on a structure, so that we can design or we can understand the behavior of the structure and we can design a structure. We will cover the materials, basic materials used in the general construction, like earth, masonry, timber, steel, concrete. Concrete itself can be either RCC or pre-stressed concrete, aluminum, glass, similar materials. Then we will also understand the loads on a structure. The loads are nowadays termed as actions. The code will code, IS code or any international codes will code a load as an action. So the actions can be a permanent action, a dead load, a variable action, that is an imposed load or a wind load or a seismic load. It can be a crane loading on a structure. It can be an accidental loading which is not expected at the time of design, or it can be moving loads like vehicles on a bridge. It can be a static load or a dynamic load, and the variations are so large that is to be dealt by the civil engineer. We will cover the seismic design, the design and detailing against the seismic load, basic concept of seismic design. Seismic loading is a totally different conceptual loading as far as civil engineering is concerned, totally different from other type of loads in a structure. So we'll try to cover the different stages in the design of structures, starting from the concept design, modeling, analysis, design, detailing, as-built drawings. Unfortunately, our syllabuses does not cover the initial and last part of this. And the syllabuses cover model analysis and design well in detail, but they lack in the concept design, wherein the student should be able to place a structural system inside a building or a bridge or a structural load path into a structure. And the syllabuses also does not give the knowledge on detailing and as-built drawings that is beyond the design. That is, you have the area of steel or a cross section designed from theory, either in steel, concrete, or pre-stress, but to put it on a drawing in such a way that the members can be jointed properly, so that a buildable structure is formed, or in an RCC or reinforced concrete, how to place the AST calculated at top, bottom, or as a stirrup, whichever shape, that is called the detailing. This part are not covered well in the syllabus, and as such, when they come out of an institute, actually the field in which they are expected to be given a job, who will look for this part of knowledge more than what they learned in the colleges, that is modeling, analysis, and design. Modeling, analysis, and design, our students who come out of the colleges are very good, excellent, but they lack a lot in concept design, they lack a lot in detailing and how to prepare the as-built drawing. Now, construction methodology, we will try to cover how different methodologies that is used in the construction, like a cast in situ construction, precast construction, site fabrication, shop fabrication, pre-engineered buildings, like that. Also, towards the end of the series, we will try to cover the professional ethics that is supposed to be observed by a civil engineer, the code of conduct for engineers, as we call it. Okay, we'll start with a definition of a structure. A structure is nothing but a device for channeling the loads, or that result from the use of the structure or from the mere presence of the structure into the supporting ground. As we know, just by building a structure, even though it is not put into use, we are creating certain loads by the construction itself. That is the self weight of the structure, or it is blocking the wind and as such a wind load is generated, or we are building a mass when we construct, and an earthquake can create a inertia load on the structure, like an acceleration from the earthquake, resulting earthquake can move, when it moves through the soil, will intercept with the structure and create a force, inertial force within the structure, mass into acceleration, just like our Newton's law, F is equal to ma. So the structure is supposed to, if I want to carry a loading at some requirement, architecturally we can plan it, but beyond that, we should build, civil engineer should build the original load path or the systems, the bonds to the structure, so that the load will stay there at the point of use without failure, without collapse, and without any issues with the deflections and vibrations and things like that. So devising such a structure is the role of the structural designer. So the structure can be there in any field of civil engineering, like it can be a transportation field, there can be a bridge, it can be a tunnel, it can be a tank for a environmental engineer, it can be a building, or it can be a chimney or similar any structure. So devising such a structure, giving its geometry, giving its to suit the original construction, original design intent, and to give it sufficient strength so that during the use of the structure, it will stand against all the expected loads, like its dead load, live load, or so-called earthquake or the cyclones, or the structure has to stand for a time, like its lifetime. If it is a building, it may be 60 to 100 years. If it is a bridge or similar structure, it may be to 100 to 200 years. So during this period, a lot of loading can happen in the structure. All these things are to be considered at the time of design. So a structural engineer designs the structural systems and structural elements in the buildings, bridges, stadiums, tunnels, or other civil engineering works. They work as the bonds of the structure. You can see several types of structures. This is a tensile membrane structure. You can see the roof, which is totally, it's a stadium, which is totally a tensile membrane. This is another tension predominant structure, the cable stayed bridge, where the cables are in full tension and the spanning bridge is in bending. So the structural design process is determination of the location, material, and size of structural elements to resist the forces acting in a structure. So that process is called design. It does not, the design is not just like a mathematics or a statically determinate thing, like you get an answer directly. When you add 2 and 2, you get 4. But design is always an iterative process. So it involves certain unknowns, certain parameters. For example, if you design a building, initially you have a data of requirement. Maybe you require a structure of length of 10 meter, width of 20 meter, like that, or number of floors, 3 floors or floors. But at the start, you don't know the total loading acting on that. So one load, like its self weight of the structure, will be decided only after you design the members, put the column sizes, beam sizes, slab thicknesses, like that. So initially we assume certain values based on our previous experience and put some structural systems, and during the course of design, the iterative process will slowly improve the original design, and finally we come out of something that is constructible. We will see the process in this in the due course. What are the way in which we arrive this iterative process. The structural design deals with safety. Safety is the factor of safety we provide to a structure such that when the structure is loaded to the expected levels, it performs with all safe requirements. It also deals with the serviceability. Serviceability is just because the structure has got enough strength, it does not mean that the structure can be used. For example, if you are walking on a slab, you get a lot of vibrations, or you get some you see some cracks on the slab, you may not feel it is safe to walk on. So the general public should be feel safe and serviceable a structure. So beyond the safety, the structure should give a feeling of safety. That is the serviceability. So it should not deflect excessively, it should not vibrate excessively, it should not have large cracks, so that the user should not feel that there is certain element of unsafety in that. So that is called serviceability. And then buildability. Just because we design any structure, it does not that mean that we can build it in any shape. So buildability should be integrated into all the structures, so that we should be able to complete the project with available materials. Maybe some design you design with some angles, some channels, some I-beams may not be available in the market. So these are the things that is counted in the buildability. You are constructing something in a workshop and trying to bring it to the site. Maybe the rods or the access is not adequate for that material sizes to get into the size. So these are all involved in the buildability. Again, economy is the most important parameter. If a builder or a intended user, whether it is government or a private person, is building a structure, he should look for the minimum cost solution, optimum cost solution in the construction. So the economy comes in. The economy cannot be the initial economy alone. A structure has got an initial cost as well as a lifetime cost. We may spend X amount of money in the starting, but if we build the structure that is too expensive to maintain, during the life of the structure, 60 or 100 years, we may be spending much more amount on that as the lifetime cost. So to protect the total cost to remain controlled, the economy has to be looking into both initial cost as well as long-term cost of the construction, lifetime cost of the construction. Sustainability is the most important thing now, that you all know that the carbon footprint is getting very priority. Everybody is talking on that, climate changes. So we all will our civil engineering is one of the area which is capable of controlling the carbon footprint to a minimum or environmental damages to a minimum, because the concrete is a material which is used by volume is the second to water that is used by the mankind. The most used material by mankind is water. The second one is concrete. So as such, if we make some saving on the concrete, it is a huge saving for the globe, for the earth. So we try to save on the energy intensive material like cement, like steel, and even the environmentally damaging things like our aggregates and the sand and all those things. And it is nowadays say that a sustainable structure is the minimum mass structure. As the mass of the structure go up, the amount of material that is spent for making the structure stand by itself, itself is more. So as such, the sustainability is a very important parameter that is looked into nowadays. Now, as we discussed, the design has got several stages. Concept design is the start of the design. When you get a building plan, a residence, or an apartment, or a commercial building, or a bridge, we start with the concept drawing. We should think of the load on the structure. We should think of the load path through which the load can travel to the bearing stratum. Normally, all structures are bearing on the soil below. Some of the structures having excess loading, we may transfer the load down to the rocky strata, much below the earth. So the concept design deals with different possibilities of transferring the load to the foundation within the functional parameters. And so all these things are identified and studied in the concept design stage. The economical and sustainable concept, the model, that is, we make multiple models in the concept design stage for a same structure, of which the most economical and most sustainable one is chosen for further study before going into the detailed design. This part is not covered well in our syllabuses. Probably at a later stage, we will try to cover some of the dedicated classes on the areas where our syllabuses are silent, but our field, the job area where our students are looking into, is expecting certain knowledge for those areas. I'll give you a simple example of a concept design. In order to support a point load, we have several options. Like we can put a beam on the top with 2 posts, or we can make a frame like a column beam frame. Here you can have 2 masonry or concrete posts, then put a beam on the top, either stone or a concrete beam or a steel beam, put a load on the top of that. So the beam is simply supported on the top of the column. For a second case, you can make a full frame, either steel, concrete, timber, or any material, and put the same load on this. You can see the material that is used here is much more than this. So conceptually, it is shown with thicknesses, but even when we calculate it, we will see that a frame will more efficiently carry the same load that may come on the post and beam. Now, the same load at that height, we can also support by using a cable. The cables, arches, etc. are membrane loaded structure, in the sense there is no bending in that. When you put a load here, it induces certain direct membrane tension in the cable, and as such they are more efficient to carry the load compared to a beam or a frame. So a suspended cable. So the concept design stage, we identify the different systems that can carry the required loading that is expected to be carried by the structure, and then choose the most economical and the most sustainable one that can be used for the final discussions, designs, detailing, and construction. Also, the different materials that can come in this process, you can use earth, You can use masonry. You can use timber, steel, concrete, aluminum, plastic. See, the list is endless. All these things are to be dealt by the civil engineer. Of course, we give thrust in the college as well as outside to probably steel and concrete. But beyond that, we have so many materials that can be used in the structural engineering and being used in the structural engineering, which is we are expected to have certain amount of knowledge on all the materials, how they behave and what are the different behavior like linear materials, non-linear materials, elastic materials, non-elastic materials, and elastoplastic materials. We will see how they behave and all in the down the lane later. Now, earth as a material, there are so much construction done. Being volume wise, earth is one of the biggest volume that is used. You can see there are earthen dams. If you think of Kerala, there is a dam in Munnar called Anirangal Dam, one of the first dams, earthen dams in Kerala, British period. And then there are in everyday life you might be seeing this approaches to a bridge. That is, the approach to the bridge is the two side roads that take you to the bridge. So that is made up of reinforced earth. The earth is inside, it is reinforced also, just like our reinforced concrete. This is a reinforced earth approach road. So earth is used in several ways for the construction. You can see a closer view of the reinforced earth wall. Inside is the earth fill that is used for the approach road, and this is the fascia wall. Masonry is also an important material that is used by us from very olden times. If you look at the pyramid of Cheops, that is around 481 feet tall. That is as good as a 40-story building nowadays, which was built before Christ BC, and it made of huge masonry blocks placed one over the other by thousands of slaves working. They don't have any machinery at that point of time. They had to work from their own available technology and available method of transportation. And it remained the tallest structure till 1907, when the 612 feet, 47-story Singer skyscraper was built in New York, America. So it could stand for thousands of years as the tallest structure. There is an image for the typical pyramid structure. You can see it is made by stone blocks placed one over the other, but with a very stable shape, most ideal shape against earthquakes and cyclones. Now the masonry as well as categorized into different things like rubble masonry using rock pieces, brick masonry, cement blocks. Nowadays we make the cement aggregate put together as a block form to substitute the building units for the masonry. There can be hollow blocks. If you look at the Great Wall of China, which the image is shown here, it is fully made of masonry, probably the longest structure in the earth that is made of masonry. As far as Kerala is concerned, Kerala, the Mullaperiyar Dam, as you see in this image, is also a purely masonry structure. You can see a close-up view here showing the image of masonry where the plaster has not there. So it is a pure masonry structure. Now, beyond that, masonry is a very powerful material as a compression carrying element. Now, there are compression only structural systems at some point of time when masonry has been used extensively for construction. Roman arches are an example. Here you can see some Chinese bridges which was built in AD 600, old, and then they are all pure arch compression only structure. So the advantage is that that does not require any tension carrying member, pure compression elements. Now coming to timber can carry flexure, shear, tension, compression, or torsion. Masonry can carry only compression, but here when you come to timber, is a much more versatile material. You can substitute it for the flexural element. You can substitute it for the shear element. You can use it in areas where tension is there, compression is there, or torsion is there. Now it is very light. It is seismic resistant. Whatever the light material available, they can be used as a seismic resisting element, because seismic load is nothing other than force into acceleration that is coming on the structure. The mass into acceleration coming on the structure, mass generated from the structure by construction, and the acceleration coming from the earthquake. So lesser the mass, lesser the seismic load. The timber is also fire resistant compared to steel. Steel, as you know, when it heats up, it loses its strength. And timber, of course, get some fire, but when it's peripherally placed areas, that is the surface of the timber, when it get into fire, it made to carbon or coke, and then this prevent further heat transfer into the core of the structure, thus becoming a very fire resistant element along the periphery, and it is more fire resistant than timber. Now coming to steel. Steel as a material very extensively used, and steel is also used as a reusable material. If we put steel into a structure, not like concrete, unlike concrete, you can utilize the steel even after the life of the structure, because if you put 100 tons of steel in a structure, you get all the 100 tons at the end of life of the structure, which means the usual cost increase in the field will give you the remaining cost that at the end of life of the structure as good as its original construction cost, or better sometimes if you use steel. Of course, initial cost of steel is slightly above the more than the concrete building, and as such, as I told you, there is initial cost, lifetime cost, all put together, total cost. So the advantage of steel is that you can easily join them by welding or bolting. Welded joints are possible. Steel as a material comes to us for construction either as the rolled sections or as reinforcement bars. Steel also comes as very high strength material, the wire ropes for the pre-stressed concrete construction. So the pre-stressing steel, or the so-called strands, is very high strength steel. Our normal mild steel has got around 250 Newton per mm square as our yield stress, whereas our pre-stressing steel gives us 1800 Newton per mm square as the yield capacity. So it is almost 6 to 7 times that of the mild steel, the pre-stressed steel. So the advantage is that more the strength capacity, you can use lesser materials. Now, steel when you use is having steel in tension is very efficient, but when it is used in compression, very short columns in compression, they fail by compression yield. If you compress the material from both sides, it tend to yield and fail. Whereas a very long column, the same compression you put on either side, it tend to fail by buckling. You can imagine how it buckle, it bends. Buckling is a process in which the bending deflection happens perpendicular to the axis of the member. So buckling is different from bending. Bending is a process in which the deformation is along the load. So if this member is bending, it has got a horizontal load here. The bending happens along the load. Now here the load axis is this, deflection axis is perpendicular to that. So buckling is differentiated from the bending by direction of deflection. If the direction of deflection is along the load, it is called a bending problem. If the direction of deflection is perpendicular to the load, it is called a buckling problem. Now, as I told you, the fire resistance of steel is slightly low. Now, as you look at it, the fire resistance normal stress strain curve of a on the y-axis and the strain on the x-axis, the stress strain curve is something like that. It goes all the way up to the yield stress, then it elongates. Some of you might have done your laboratory test in tension test, like using a UTM, universal testing machine, and you might have taken the graphs as well, or if you have not done, probably in a year you will be doing. So you can see this phenomenon. Now assume that we are heating up the same specimen. Now as you heat up the same specimen, you can see this yield level, which is around 250 Newton per mm square for a mild steel. It remain, if we plot this yield at different temperature, if we plot temperature on the x-axis and the yield stress along the y-axis, the steel yield at 250 Newton per mm square will remain almost constant up to 400 degrees. Now, beyond 400 degrees, it sharply reduces. You see, at 800 degree or more, the yield stress is less than 20 Newton or 25 Newton per mm square, in which the structure is unable to carry even its self weight. So if you get a fire in the steel building, once the structure heats up, it will not be able to carry even its self weight. So the steel is very weak in fire resistance. So we will have to do certain fire protection before we can use the steel. This fire protection is one of the additional cost for using a steel structure. Now we can see the fire protection typically used. It can be a concrete encasement for the beam. You can see a slab above, a beam here. It is protected with a concrete around that, so that when the fire happens, the concrete will prevent heat reaching the steel beam, so that when the steel beam, when it is less than 400 degrees Celsius, it can carry full load capacity. So that is the principle of fire protection. We isolate the structure from the fire. If a fire happens, it will not be allowed to heat our structural element. Now, this is another way of making a partially encased beam for fire protection. We make a masonry infill in the web of the structure, so that some area will get heat up, but still there is the core of the beam will not be getting heat up when it is protected with the masonry. It is much easier to do this sort of fire protection compared to the earlier one what we discussed. So this is also widely used. Now the steel, there is what is called the lateral stability is important. When a steel beam, you can assume I have shown a cantilever beam fixed on the wall. Then I'm just loading it at the tip using a dead load applied vertically. Now, if the beam is simple lateral beam, in unloaded position, it is a straight beam. When it is loaded, it not only deflects downwards, it twists, it deflects laterally as well, because this is called the laterally unstable beam. This is because it has got a y-axis moment of inertia much less than the x-axis moment of inertia. So if the structure is confined on its wings, then this sort of buckling will not happen. So the lateral stability is important for the steel beams, and such a problem is not there if the beam is loaded with its along its weak axis. This I-beam has got two axes. This is the major axis of the beam, and this is the minor axis of the beam. So if we load on the major axis, this buckling will result. But if we can load the structure on the minor axis, this sort of a lateral buckling will not happen. So lateral stability of the beams is very important. So another one is local buckling. The beam can have a buckling. As you remember, we have discussed the buckling as a full element between the ends of the column in a previous slide. It is buckling from one end to the other end. So that is called the global buckling. Now, if a flange of the compression flange of the beam alone is buckling, this is called a local buckling. So the beam should be capable of carrying the load without global buckling, as well as local buckling. Both should not happen. Now, this was not covered in the previous steel construction code, IS 800, which was 1984 version. And in 2007, when the IS 800 has revised, it included the provisions for how to deal with the local buckling. So now the current IS code, we have provisions for design how to check for local buckling and how to prevent local buckling. Okay. Now from steel we come to the concrete. Rajiv, up to what time we can go, Rajiv? Nafi?
You are on mute, sir, Reggie, sir. I think 8:50, sir. 8:50.
8:50. Okay, good.
Sir, you are on mute. Reggie, sir, you are on mute.
Yeah, I was telling like you can take up to say 5 minutes questions we can expect. So 8:55.
Okay. Fine.
8:50 or 8:55, yes.
Okay, good. So concrete, beyond steel, concrete, as we discussed previously, concrete is the most widely consumed material by mankind after water, as we discussed previously. So concrete has got very important as far as the civil engineer is concerned, because it comes into the picture whichever field we engineers work, whether it is transportation or transportation field. It's a major component in tunnels and bridges, buildings, and in environmental tanks. When we work with either water supply or the sewage treatment or whatever field, lot of tanks and the conduits, all the areas, concrete is a major material. Now the strength of concrete has gone to unimaginable level that the mankind is able to generate M200 grade concrete nowadays. It's a dream that our steel has got only if 250 Newton per mm square yield strength, but concrete could reach up to original. We use M20, 25 like that we study in the classrooms, but advanced areas, the concrete has come out as 200 Newton per mm square as the strength. So M10 to M200 grade is available. And it is used to build every other structure, including the tallest building now, the Burj Dubai. The concrete can be either site mix or ready mix. It means it is either factory made or site made. In the site mix, we get the basic materials to the site and then mix them in a mixing machine or manual mixing, and depending on the volume required, and then we use it at site. Whereas the ready mix, the mixing happens in the factory, then it is carried to the site with some special chemicals added in that to prevent setting, like retarders, and then through a truck transit mixer, which is still rotating when it is transporting the concrete, and when it is reaching the site, we pump the concrete to the required location. So that is called a ready mix concrete. The concrete can be either precast or cast in situ. Concrete structures sometimes as a whole is ready made at factory and transported, like a column, a staircase, a beam, a slab. All the elements can be readily cast at a factory, so that they can be controlling the quality, they can be cured properly, and then they can be transported to the site and fixed and jointed. The concrete can be cast in situ also. That is the first one we discussed. The site mix and ready mix will give us the cast in situ concrete. We place the formwork and then cast the concrete at site. Whereas the precast case, the forms are in the factory, concrete is made in the factory, then it is cured in the factory and then transported to the site. Now, the concrete, the primary problems, they are very massive, they are very heavy, So it is not that seismic friendly, but of course it is used widely in the seismic areas as well with adequate precautions. We will see down the lane. Concrete has got both short-term loading, short-term deflections as well as long-term deflections. This is a different thing that concrete is exhibiting compared to other normal materials used in the construction. That is called creep. Creep is a special property of concrete, wherein if the concrete is loaded to certain level initially and it is left there without increase in the load, keeping the same loading on the structure, after a period of time, the deflections increase. This process is called creeping. So creep is a property exhibited by not only concrete, several other elements as well, but concrete is the most important material that is exhibiting creep as far as the construction is concerned. So the long-term deflections are different and to the tune of almost double the initial deflections. When we de-shutter a concrete structure, we get X deflection. After 5 years, if we go back and measure, it may be 2x. So this increase in deflection is a concern and has to be accounted in the original design and construction. We have several methodology. We'll discuss some of them. Now, concrete is normally strong in compression, but the tension that is coming in the concrete part is carried by the reinforcement that is put inside. Now, this reinforcement is made of steel, and as you know, steel, when it is left to the environment, the corrosive elements in the atmosphere attack it. That can be carbon dioxide, that can be sulfur dioxide, or any other acidic oxides that is coming in the atmosphere will attack this concrete. So we give what is called cover to the steel. The cover is that we place the steel within certain depth inside the concrete element such that it is protected. We have seen that the concrete is protecting the steel from the temperature increase and the fire loading as well. Here, the concrete cover is also used to protect the steel from the environmental corrosive action. So depending on the exposure which the structure is subjected to, it can be a mild exposure like when the structure is protected within the building limits, or it can be a moderate exposure like a bridge, or it can be a severe exposure when it is put to a sea coast, or it can be an extreme exposure if the structure is put right at the sea where the sea splash into the structure. So all these things are different exposures. Depending on this environment to which the structure is exposed, we give sufficient concrete strength, sufficient concrete cover so that it can provide us adequate protection. As we already discussed, the cover is also provided to suit the fire resistance. If you want 1 hour fire resistance, 60 minutes, it is given certain cover. And if you want 2 hour fire resistance, it is given more cover. It depends on how much time we require. The inhabitants of the structure can be safely escape from the structure in the event of a fire, and it depends on the time by which a nearest fire force people can reach the building. So based on that, we say that the structure will have a fire resistance of 60 minutes, 120 minutes, like that. So depending on that, we adjust the cover so that it gets adequate fire resistance. So basic concrete is made of a binder. It may be cement or a different material, geopolymer, cement, and several other materials. Water plus aggregates plus additives. Aggregates are either rock aggregates, sand aggregates, natural aggregates, or made aggregates, man-made aggregates. Then additives are property modifiers for concrete. The property modifiers are quick setting, slow setting, strength, quick hardening. It can be waterproof admixtures. It can be bonding agents. It can be non-shrink chemicals. So many things. Like just like a medical shop, you get the modifiers and the medicines that is added in the concrete mix from a shop. 200, 300 categories by different manufacturers. So much additives are there. So that itself is a big study for civil engineer nowadays, the concrete technology. I think Rajiv will stop with this today, 8:55. We'll continue in the next class.
Yes, sir. Thank you. Thank you for a great class. I will now request the students to ask questions. It's a great opportunity for you to ask questions to the master. Also, I would like to, announce the presence of Harish Shankar, who is the son of Suresh sir. He will also be taking classes. He is also an established senior structural consultant working with him. Thank you, Hari, for joining the class. Okay, students, now please shoot your questions.
Hello, sir. Hello.
Yes, yes.
Sir, why does this creep happens in concrete, sir?
Yeah, creep is a material behavior exhibited by some of the materials, many materials, in fact, some of them when used in the concrete, used in civil engineering, that exhibit, not concrete alone. Now, this is a molecular level movement, or it's a behavior or a property of the material. So concrete, unfortunately, has got that nature or that property. It's a basic molecular movement under stress. You constant stress, when the molecules readjust itself, we get excess strain. That is the increase in the strain without increase in stress. That is called creep. So it's a material property. Of course, we have certain methodologies to reduce creep. We cannot eliminate or avoid creep, but we can have several things like long-time curing, modification of the material components in the concrete, and things like that to reduce creep.
Okay, sir. Thank you.
Good evening, sir.
Yes.
So my question is that I have doubt why fly ash concrete is not commonly used.
Now, fly ash concrete is widely used. To be precise, it is preferred also. It is not that it is not commonly used. It is widely used because fly ash has got certain properties which give us the advantages of crack reduction. It is more sustainable or environmental friendly because it is utilizing a waste material. It reduces the cement content, the OPC content in the cement, and it is not that it is not sparingly used. It is widely used. I think now OPC is one which is sparingly used.
Thank you, sir.
May I know who all have asked questions? Can you tell your names?
Sir, Advait Vishnu Prasad.
Advait. And second one?
Sajna Assis.
Okay, good. Thank you for asking questions. Anybody else? Any questions? Anything about, civil engineering, your future, what you want to do, and anything? You'll be a best person to answer anything under the sun.
Like that, civil engineering.
Yes, with respect to Lady Madam, any questions?
No, not
To-
particularly any questions. It was a good class for the beginners. I hope they followed all what is steel, what is concrete, what are the materials used. Any doubts, please ask.
Okay, thank you. So it's 9 o'clock. We'll conclude. Thank you once again. Thank you all for attending and making it a great success. Thank you.
Thank you.
Thank you.
Thank you,
Thank
Raji. Thank you, students, for the
Thank-
attendance. We'll see you in the next